Revise this reaction from nitriles and amides. Nitriles are also called as cyanides. So any alkyl nitride, when it is hydrolyzed, we get first this intermediate, and this intermediate after tautomerization, amides are formed. These amides, after acidic hydrolysis, we get the carboxylic acids. Means this is the best method by preparation of carboxylic acids by using amides. Then Sanskruti Bhosle, switch off your video. Yes, I will take another example, ethanamide. You know how the amides are prepared now. Amides are prepared by using nitriles. Nitriles on hydrolysis gives intermediate after tautomerization, amides and amides to carboxylic acids. So directly if the amides are given, amides on hydrolysis, they give acids. So we can take any example of amide. This is benzamide, benzene, CONH2. This is benzamide. Acidic hydrolysis, H3O plus means this is acidic hydrolysis, H2O in presence of acid. This gives benzoic acid plus ammonia. So at your home, you can take any benzamide and we can prepare any benzoic acid. Next one, by using acyl chloride and anhydrides. This is a very easy method to prepare the carboxylic acid, just hydrolysis. By using water, the OH minus from this water attacks to this carbonyl carbon, and this Cl will be removed. This Cl will be combined with one hydrogen, and we get HCl molecule and carboxylic acid. So this is a very simple method. By using, we can prepare the carboxylic acids by using acyl chlorides and as acid anhydride. This is again the same process. In this H2O, it is very difficult to explain the mechanism by using without using the board. So in this water, HOH is there. So O minus attacks to this carbonyl carbon because this is electron deficient. We'll get the negative charge here. Again, this negative charge will be resonance, and this COO bond will be broken. We get two molecules of carboxylic acid when these R groups are same. If these R groups are different, we get two different acids. See, one example is given here. One example is given. In this example, this is a benzoic anhydride. We get benzoic acid. And if the two different R groups are used or AR group is used, this is a benzoic ethanoic anhydride, C6H5. This is a benzoic and this is a ethanoic anhydride. We get two different acids here, benzoic acid and ethanoic acids. So depending upon the anhydride use, we get the acids just by using hydrolysis. So next one is by using esters. Esters are also the same, like hydrolysis takes place by using anhydrides and acyl chlorides. So first, I will take general example. I will explain the general reaction of esters. Take any esters having this COO group. This is a functional group of esters. Esters on hydrolysis with dilute mineral acids like HCl or H2SO4. we get carboxylic acids and the mixture of alcohols here. So we will take the one example of esters, ethyl benzoate. This is a ethyl group attached to the oxygen. So we have to take first this ethyl, and this is a benzoate group. So this is ethyl benzoate. On acidic hydrolysis, we get benzoic acid plus alcohol. Any esters after hydrolysis, they give a mixture of carboxylic acids and alcohol. You can take any esters here. Then alkaline hydrolysis of esters. You know, in 10th standard, we already learned about the alkaline hydrolysis of esters are called as soaps. So today I will explain how the soaps are prepared. Esters on hydrolysis with alkalis. Alkalis we have taken in this reaction is dilute NaOH or dilute KOH. Both these are alkalis to form the solution of water soluble sodium or potassium salts are prepared here. See, this is a methyl propanoate. This is methyl and this is a propanoate because 3 carbons are there. Methyl propanoate plus dilute NaOH. Dilute NaOH indicates this hydrolysis is in presence of base. So this NaOH, ONA, this attacks here. O minus attacks to this carbonyl. This OCH3 group is removed. This CH3O combines with this hydrogen and alcohol is formed. But this main product is called as, this is a sodium salt of fatty acid. See, this is a Na plus and this is a O minus. So it is a salt, sodium propanoate, it is a salt. This sodium propanoate after hydrolysis, we can again get back the acid. So this sodium propanoate plus H2O, again in presence of acid, we get the free acid again. So by using this salt, again we will get the acid by using hydrolysis. So one example, another example is taken here. This is ethyl butanoate. The ethyl group is attached here, COO. This is C2H5, ethyl and butanoate. Why it is butanoate? Because there are 4 carbons, 1, 2, 3, 4. Ethyl butanoate in presence of NaOH. This is the alkali. We get here first salt. This is the sodium salt of carboxylic acids, and after hydrolysis, again we will get back the free acid and alcohol here. So sodium or potassium salts of higher fatty acids are called as soaps. Hence, alkaline hydrolysis of esters is also called as saponification. Saponification is nothing but the method of preparation of salt. So remember this saponification reaction. For the examination purpose, the question will be asked like this: explain the saponification reaction or saponification process. So alkaline hydrolysis of esters, remember, esters can be hydrolyzed by 2 ways, by alkali and by using acids. So make a practice at your home, take 2 examples by using acidic hydrolysis and by using basic hydrolysis. In alkaline hydrolysis, we get the salts, but in case of acidic hydrolysis, we didn't get salt, directly we'll get the mixture of carboxylic acids and alcohols. And in this hydrolysis process, we get sodium salt. After hydrolysis, we get acid and base back. Then next method of preparation of carboxylic acid is by using alkyl benzene. We will take alkyl benzene, you know, to the benzene ring. When the alkyl group is attached, any alkyl group, it is called as alkyl benzene. Aromatic carboxylic acids are prepared by using this method. By oxidation of alkyl benzene by the oxidizing agent like KMnO4. There are many oxidizing agents. KMnO4 is there, then chromic acid is there, copper powder is there, then K2Cr2O7 is there, then Na2Cr2O7 is there. All these are oxidizing agents. When this toluene is treated with a strong oxidizing agent like KMnO4 in presence of alkalis, we get here first salt. Potassium benzoate salt is prepared, and this salt after hydrolysis we get benzoic acid. Directly in one step you can show at the time of exam, toluene when oxidized we get benzoic acid. Directly we can show in one step. This is cumene. In chapter number alcohols, phenols, and ethers, you know this cumene already know. It is also called as isopropyl benzene. This cumene, when treated with KMnO4, means it is oxidized. Again, we will get the potassium benzoate here, and after hydrolysis, we get air benzoic acid. The main drawback of this reaction is tertiary alkyl substituent on benzene is not oxidized because there is no hydrogen. If there is no hydrogen is there, the oxidation cannot take place. Then from alkenes, so carboxylic acids can be prepared by the oxidation of alkenes by KMnO4 and dilute H2SO4. You can use any oxidizing agent here. If KMnO4 is not available, you can use CrO3, you can use copper. But oxidation reaction takes place here. This is a styrene. Another name is phenylethene. This is a phenyl and this is ethene group. This is also called as styrene. We get directly benzoic acid, means this CH double bond CH2, it gets oxidized. If cyclohexene is there, this ring is broken and we get here two COH groups. Adipic acid is formed. Adipic acid means it is a 1, 2, 3, 4, CH2 4 times, CH2 4 times and COH. CH4, so 1, 2, 3, 4, CH2 4, COH, COH. It is called as adipic acid. Hexane 1,4 dioic acid, another name is 1, 2, 3, 4, 5, 6. Hexane 1,4 dioic acid, DIOIC, dioic acid, because there are two COH groups. Then from primary alcohols. Primary alcohols, this reaction is already completed in many times. Oxidation of this alcohol, we get first aldehyde and aldehydes on oxidation, we get the carboxylic acids. This reaction is already we learned in this chapter also, in chapter number 10 also. Again, I will explain. Primary alcohols are oxidized to give plus aldehydes. And aldehydes on oxidation, they give carboxylic acids. If the strong oxidizing agents are used, we directly get carboxylic acids. If the mild oxidizing agents are used, alcohols on oxidation gives aldehydes first, and aldehydes on oxidation gives carboxylic acids. If the strong oxidizing agents like KMnO4, then K2Cr2O7, then CrO3 in acidic medium, these are specifically called as Jones reagent. So in the last 2 years, one question is asked for the JEE or NEET exam. What is the action of Jones reagent on alcohol? So purposefully I have mentioned this word here. Jones reagent, in your textbook it is not mentioned, but for the JEE and NEET exam, the question is asked on this. So what is Jones reagent? I will explain again. The oxidizing agents like KMnO4 or alkaline in acidic medium or alkalic medium, or K2Cr2O7 and CrO3 in acidic, all these are called as Jones reagent. Jones reagent means oxidizing agent in case of alkaline medium or acidic medium. This combination is called as Jones reagent. So alcohols with Jones reagent, they give carboxylic acid. Directly they do not give carboxylic acid. One step is there. Aldehydes are formed, and aldehydes directly they oxidize because this is strong reducing agent. Strong oxidizing agent. They gives RCOH. If instead of this alkaline KMnO4, if PCC is used, pyridium chlorochromate, the reaction will stop. The reaction will stop at aldehyde stage. We didn't get the carboxylic acids. So for the preparation of carboxylic acids, alcohol should be oxidized with strong oxidizing agent. One example is given here, ethanol. All of you know the ethanol is also called as ethyl alcohol in presence of this K2Cr2O7 and dilute H2SO4. First see here, aldehyde is formed. Means in this reaction, two steps are shown here. Two steps are shown. First step is preparation of aldehyde, and aldehydes on oxidation they gives ethanoic acid. Then from the Grignard reagent, this is very important mark there. This reaction is very important. I think 12 to 13 times this reaction is asked for board exam. So I will explain in detail. Please concentrate. This is addition of Grignard reagent in solid CO2, or it is also called as a dry ice. So I will explain in detail. Please concentrate. What is mean by dry ice? What is solid CO2? Grignard reagents in dry ether. Always remember, when Grignard reagent is there, automatically dry ether will be there, because dry ether is used as a solvent which do not react with Grignard reagent. Now, the Grignard reagent is treated with dry ice or solid CO2. Solid CO2 means the carbon dioxide in solid form. This is called as a dry ice. In presence of dry ether, this is a general reaction. It is intermediate is formed, and this intermediate, after hydrolysis, we get carboxylic acid. First, I will explain how this intermediate is formed. You already know this RMgX Grignard reagent, in which this R group is having negatively charged, delta minus charge, X is having delta minus charge, and this Mg having 2 delta plus. So the entire Grignard reagent is neutral. This is 1 minus, this is second minus, and this is 2 delta plus, so it will be neutralized. So for the reaction, this R minus, it will attach to this carbon, carbonyl carbon. So after attacking this R group to this carbonyl carbon, this carbon oxygen double bond will be broken. This electron density will be shifted on this oxygen. So it will be O minus. When this is O minus, it will attach to remaining MgX. So we will get the intermediate here. R, it will be bonded to the CO, this CO, RCO, and OMgX. This MgX, it is from this Grignard reagent, because it will be broken. This bond will be broken first. This R will attack to this carbonyl. So the bond between this CO, it will be broken. Negative charge will be appeared on this oxygen, and this oxygen will attach to this MgX. So this intermediate is formed first, and then after hydrolysis, this RCOOH, this RCOOH bond will be formed. This OMgX, this is OMgX, and one hydrogen from this water is attached here, and we'll get the carboxylic acid. Again, I will take one example. I will take 2 more examples, because this is very important reaction. Many times it is asked for board exam. Many times, remember. So this is the phenyl magnesium bromide. This is phenyl magnesium bromide. Again, this is Grignard reagent. So in this Grignard reagent, this phenyl will attack. This phenyl will attack to this carbonyl carbon. The bond between this CO, it will be broken. It will be O minus, and this O minus will attack MgBr. We get the complex here. So this benzene CO, see this benzene CO, O minus, it will attach to MgBr. So OMgBr will be formed. Instead of this X, any halogen will be attached there. So this intermediate, after hydrolysis, what will form here? This benzene COOH. This OH will be formed. Plus this is byproduct MgXOH. This is benzoic acid. So if you understand the mechanism of this reaction, you can prepare any carboxylic acid by using this Grignard reagent. If this Grignard reagent will be changed, the acid will be changed. Instead of the phenyl magnesium bromide, if the ethyl magnesium bromide is used, the acid will be ethanoic acid. So the homework is given to you. This depends upon the previous reactions. So solve this homework at your home. These are the simple reactions are given, which are asked for board exam and also for the JEE NEET, because I am taking these questions from different books, not from your textbooks. So the answers are also given. If you didn't find the answers of these questions are also given here. So after finishing the lecture, read the questions carefully, and try to write the answers. Those students who want to get out of marks in chemistry, please daily complete this homework. Then again, some questions are given. They predict the products and the name of the structures of the following. All these reactions are, see, this is a cyanide dilute HCl, we get amide first, then amide to HCl, we get the carboxylic acid. Then this is a oxidation KMnO4, directly we get here acid. This is a C6H5CO, this ester, this acidic hydrolysis of ester. And this is a dry ice, I explained this reaction, CH3MgBr, dry ice. So all these questions are very interesting. Go through that. It is very easy. It will be very interesting. Then one question is given. Show how each of the following compounds can be converted into benzoic acid. Ethyl benzene. Ethyl benzene on oxidation directly it gives benzoic acid. Then bromobenzene is given. Then acetophenone is given. Then styrene. All these are discussed. Then the next part is physical properties. No any question will be asked for board exam on this physical property, but for the NEET, JEE and CET exam, these questions are asked. Nature of intermolecular forces. Now I am coming to the aldehydes and ketones. In case of aldehyde ketones, the carbonyl bond, this is CO bond, is polar bond because this oxygen having the delta minus charge, and this carbon is having the delta. Electron density will be pulled here, so it will be delta minus, automatically it will be delta plus. Therefore these compounds contain dipole forces interaction. In case of carbonyl compound, they are having the dipole forces interaction. These molecules orient in such a way that they are oppositely polarized atoms facing each other like this. So in case of carboxylic acids, carboxylic group contains OH bond, which is responsible for the formation of hydrogen bonding. I will show how carboxylic acids show the hydrogen bonding here. Yes, physical state and boiling point of aldehydes and ketones. So formaldehyde is the first aldehyde, which is gas at room temperature and the very bad smell, very irritating odor. Then acetaldehyde is extremely volatile. It is colorless liquid. Then higher aldehydes have the pleasant odors. Acetone, which is very famous in our chemistry laboratory, which is the liquid at room temperature and very pleasant smell. But most of the higher ketones having the bland odor. So the boiling points of aldehydes and ketones we will discuss here. See the number of carbon atoms: 1, 2, 3, 4, 5, 6. Methanol, ethanol, propanol, butanol, pentanol, hexanol. As the number of carbons increases, see the boiling point is also increases. In case of ketone, it is same. As the molecular mass increases, see the molecular mass increases, the boiling point increases. In ketones also, see the boiling points are also increasing. So remember one thing, in case of aldehydes and ketones, as the molecular mass increases, the boiling point is increases. Solubility, depends upon the bonding. If the bonding is there, these are more soluble. Oxygen atom, in case of CO, can involve in hydrogen bonding in water molecule. Because of this, lower aldehydes and ketones are water soluble. If this bonding is there, it will be soluble. But lower aldehydes and ketones are water soluble. As the molecular mass increases, the proportion of hydrocarbon part in the molecule increases, which cannot form hydrocarbon bond, and therefore the water solubility decreases. So I will explain what is happening if the number of carbons are increasing. What is happening actually? As the molecular mass increases, see what will happen. The proportion of hydrocarbon part of the molecule increases. Say the proportion of hydrocarbon part means this R group is increases. And if the R group is increases, which cannot form hydrocarbon bond, and therefore water solubility decreases. Then I am coming to the physical state and boiling point solubilities of carboxylic acids. In the previous slide, we discussed about the physical state, boiling point, and solubilities of the aldehydes and ketones. So, what is happening in carboxylic acid? See in this chart, lower aliphatic carboxylic acid up to 9 carbons. Up to 9 carbons, these are colorless liquids which is having very bad odor, irritating smell. Then the higher acids are colorless, odorless, wax solids having the low volatility, means these are not volatile. Boiling points of lower carboxylic acids are given below. See, this is formic acid, acetic acid, propanoic acid, N-butyric acid, N-valeritic acid. All these are straight chain carboxylic acid. And see the boiling point here. As the molecular mass increases, boiling point is also increases. One question is asked for board exam. I will explain here. Carboxylic acids having higher boiling points than those of alkanes, ethers, alcohols, aldehydes, and ketones. This question is asked for exam. Why the carboxylic acids having the higher boiling points than those of alkanes, ethers, alcohols, aldehydes, and ketones of comparable mass? Means the mass should be comparable, same. So the reason is, in liquid phase, what is happening? See, carboxylic acids forms dimers. See, in this example, it is shown CH3COOH, CH3COOH, and this is CH3COOH. So this dimer of acetic acid means, what is mean by dimer? The two molecules are held together with two hydrogen bonds. Here, the bond between this hydrogen and this oxygen, and the bond between this oxygen and this hydrogen. So this is called as dimers. So if the dimers are formed, means if the two hydrogen bonds are formed, acidic hydrogen. So you understand the procedure of how the dimers are formed. This such type of dimers are not formed in case of alkanes, ethers, alcohols, aldehydes, and ketones. That's why the carboxylic acids having the more boiling points. Because of this dimer, what is happening? This doubles the size of the molecule. If the dimer is formed, the size of the molecule becomes double, and because of this doubling of size, increase in intermolecular van der Waals forces, and therefore higher boiling point is, the temperature is required, higher temperature is required to break this dimer. So that's why this is the reason, of higher boiling points of carboxylic acid. Dimers are formed. This such type of dimers are not found in alkanes, ethers, alcohols, and aldehydes and ketones. See here, in one chart is given here, variation of boiling point with the functional group here. See, this is the functional group of alkane is given here. Molecular mass is 15. See, the molecular mass is nearly same here. But this is alkane, this is one is ether, one is aldehyde, one is ketone, one is alcohol, one is carboxylic acid. But I want to show one important thing here. See, the strength of intermolecular forces increases from this alkane to the carboxylic acid. And see the boiling point here, it is a 272, 281, this is a 322, and this is 329, 370. See, the highest boiling point is of carboxylic acids, because the dimer is formed here, and the dimers are not formed here. So that's why the carboxylic acids having the higher boiling point. At the time of CET board exam, they will give any 4 examples, and they will ask which of the following is having the highest boiling point. So you must know the reasons. Only the carboxylic acid forms dimers. That's why the boiling points are very high. Then this is not for your exam, just for the knowledge purpose I have given. Keep in mind the strength of the intermolecular force. See the strength of intermolecular force, which bond is very strong. First one is this is very strong. Hydrogen bonds are very strong. Then dipole-dipole interaction, and then van der Waals forces are very weak. So the boiling points of carboxylic acids are very high because of these hydrogen bonds. Then alcohols, then ketones, then aldehydes, and very less alkanes having very less boiling points because of the bonding. See, the strength of the bonding is shown here. You must know these things. If you understand these things, you can solve the MCQs also. You can solve the reactivity problems also. You can solve the boiling points and melting points problem also, because you must know these things. Hydrogen bond is stronger than dipole-dipole interaction, and the weakest interaction is van der Waals forces. Then this is not for exam, this is for your knowledge purpose. I have given this, so read at your home. Then solubilities of carboxylic acids. Lower aliphatic carboxylic acids up to the 4 carbons are miscible with water due to the formation of intermolecular hydrogen bonds. When the intermolecular hydrogen bonds are formed with water, these are soluble. Then what is happening? The solubility of the carboxylic acids in water decreases. See, this is the most important thing. The solubility of carboxylic acid in water decreases with increasing molecular mass. What is happening if the molecular mass is increasing? The reason is same. As the molecular mass is increases, the hydrocarbon part. See, higher carboxylic acids are practically insoluble in water because what is happening? Due to the increased hydrophobic. Hydrophobic means this is a water hating. This is not water lovable part. Hydrophobic, which part is hydrocarbon part. Hydrocarbon part is hydrophobic, and this hydrophobic part increases when molecular mass is increases. Higher carboxylic acids means they having the higher percentage of hydrocarbon. This higher percentage of hydrocarbon due to the increase in this higher percentage of hydrocarbon part, this interaction of hydrocarbon part with water. Then aromatic acids like benzoic acids are also practically insoluble in water at room temperature. Water insoluble carboxylic acids are soluble in organic solvents. Like dissolves, like, you know the formula, water insoluble carboxylic acids will be soluble in organic solvents like ether, benzene. Means polar dissolves in polar solvents and non-polar dissolves in non-polar solvents. You must know these solubility concepts. So once again, I am explaining this is a very important in what is happening in case of higher carboxylic acids. Higher carboxylic acids are practically insoluble in water because in case of higher carboxylic acids, the percentage of hydrocarbon part is increased, and this hydrocarbon part is water heating part. It is called as hydrophobic part, and due to the increased interaction of the hydrocarbon part with water, so the percentage of hydrocarbon part is increases, which is water heating, and due to this water heating, what you can say, water heating ability of this part, this is insoluble in water. So this is applicable to the aldehydes and ketones also. When the hydrocarbon part is increased, it becomes hydrophobic, water heating part, and due to this water heating part, solubility affected. Then this question is asked for board exam October 2013. Explain the structure of carbonyl group. So what is expected to write, I will explain. Because in your textbook, many concepts are here. Don't write many things. Only we have to draw the structure. See, this is the polarity of carbonyl group. The carbonyl group is polar because of this oxygen, and this is carbon. Oxygen is highly electronegative, so it will be delta minus. In this diagram, it is shown. This is the delta minus, this is the delta plus, and these are the resonance structures are shown here. And this is a resonance hybrid is shown in figure number D. So only we have to write these structures and write below. Carbon has a positive, and it is write down it is a polar. Therefore, it is electron deficient. This carbon is electron deficient. Oxygen pulls the electron density towards itself. So the carbon is having electron deficient. So whenever the nucleophile attacks, always it attacks on carbonyl carbon because this is electron deficient. So for the 2 marks, we have to draw the structures and write only one sentence. Because of the electronegativity, this oxygen pulls the electron density towards itself, and this bond becomes polar. So it is very easy to get the 2 marks. Then reactivity of aldehydes and ketones. Reactivity of aldehyde ketones is due to the polarity of this bond. Due to this polarity, this carbon becomes electron deficient, and nucleophiles can be attacks, which results in electrophilicity of carbon. In general, aldehydes are more reactive than ketones. Now I will explain why this is happening. What is the difference between aldehydes and ketones? In general, aldehydes are more reactive than ketones towards the nucleophilic attack. So in case of ketones, both the groups are R groups. So the bulkicity increases, also the steric effect. This can be explained in the terms of electronic effects and steric effects. So in the next lecture, tomorrow's lecture, I will explain what is the why aldehydes are more reactive than ketones. Just I will give the introduction. What is electronic effects? There are 2 types of electronic effects in 11th standard. Also, we learn about the electronic effects, but we didn't concentrate there. I also given one important hint at the time of 11th standard. Remember these effects, resonance effects and then inductive effects. These are very important for the board exam, for the reactivity and for the attack of the nucleophiles and electrophiles. These effects are very important. Alkyl groups are electron donating effect. They show plus I effect. Alkyl groups. So in case of ketone, there are 2 electron donating alkyl groups are bonded to the carbonyl carbon. So what is happening, which are responsible for decreasing its positive polarity and electrophilicity. See, this in these 2 examples it is shown. This ketone having the 2 R groups. This R group will donate the electron density to this carbon. This R group will donate electron density to this carbon. So what is happening? Decreasing the positive polarity of this and electrophilicity. And in case of aldehyde, as there is only one R group,